Okay, let's dive in. You've got an exam coming up covering the vast and often surprising world of the philosophy and history of science.
Yeah, it's a huge field.
Totally. It's
Yep.
brimming with those aha moments, from ancient thinkers wrestling with the cosmos right up to the cutting edge of AI today.
Right.
Our mission today is to give you a real shortcut, I guess you could say, a comprehensive deep dive into the core of these complex topics.
Exactly. We want to equip you with the knowledge not just to ace that exam, but to really get how science shapes our world.
Past, present, and future.
Definitely. We've taken a stack of your sources, articles, research, core concepts, and we're going to pull out the most important nuggets of knowledge for you.
Sounds good.
We'll explore everything from how scientific thought actually evolved, the twists and turns, to the big ethical dilemmas we face with modern technology.
So you grasp not just the what, but the why and how behind it all.
That's the plan. Think of it as a guided tour, maybe through centuries of human inquiry, all designed to make you well-informed and genuinely prepared.
So let's start at the very beginning. I mean, how do we even begin to think about science?
Good place to start.
Our first major stop, this is Q1 for your exam prep, is the positivist tradition in the philosophy of science.
Right.
This is where the idea of science as this purely empirical, objective thing really takes root, isn't it?
It is, and you can trace this right back to Auguste Comte, often called the father of positivism.
Okay.
He envisioned science as, well, the ultimate foundation for understanding society. Comte developed his famous law of three stages.
The three stages, right?
Yes, suggesting that human thought and society itself, it progresses through distinct phases. Starts with the primitive theological stage.
Where everything's explained by gods or spirits.
Exactly, supernatural causes. And then it moves to a metaphysical stage where, abstract forces or essences are the go-to explanation.
Like nature's tendency or something.
Kind of. And finally, it reaches the positive stage. This is the key one for Comte. It's where scientific understanding, based purely on observation and empirical evidence, reigns supreme.
No more speculation.
Right. He even proposed this hierarchy of sciences, starting with abstract math and moving up to complex social interactions, thinking each field built on the last.
Interesting structure.
And he truly thought science should be anti-metaphysical, totally focused on what's real and useful, and ultimately it should serve humanity through social analysis.
That sounds like a pretty grand vision. So how did others build on that?
Well, building on Comte, you have John Stuart Mill. He's a key British positivist.
Mill. No.
His system of logic developed really rigorous empirical methods for scientific inquiry. Now, while he expanded on Comte's ideas, Mill was less focused on the collective, more on the individual.
A subtle shift.
A subtle but important divergence, yeah. He also wrestled with the problem of deductive reasoning. He noticed that conclusions often just restate information already in the premises.
So is it really new knowledge?
That was his question. But his method of residues was quite clever. It was a way to isolate unknown causes by systematically accounting for the known factors.
Ah, so you figure out what's left over.
Exactly. Helping deduce what remains after those known influences are removed. Like solving a puzzle by eliminating what you already know.
Makes sense.
Precisely. And then there's Herbert Spencer. He took a fascinating evolutionary approach.
Applying Darwin.
Yeah, he applied Darwinian principles not just to biology, which is obvious, but remarkably to sociology and psychology, too.
Wow. Yeah.
Spencer saw social systems as living, dynamic entities. They evolve, they adapt, moving from simple, homogeneous structures to increasingly complex, specialized ones.
That's a huge leap, applying biology to society like that.
It's a very grand, sweeping vision of progress, definitely. Applying a biological lens to how societies develop.
Okay, that's first positivism. Now, let's fast forward slightly. You mentioned second positivism or empirical criticism with thinkers like Ernst Mach and Richard Evanerius. How did their ideas shift this foundation?
Well, Mach saw science not so much as discovering absolute truths, but more as a dynamic, human-centered methodology.
So less about finding the truth.
Exactly. For him, knowledge emerged from these complex interactions between our perception, the technology we use, and how we abstract things. Science, in his view, was a pragmatic system
For organizing things.
for organizing and predicting our sensory experiences within these evolving conceptual frameworks.
Yeah.
It was about usefulness and organization, not some ultimate fixed reality.
So more about finding the best way to make sense of what we experience.
That's a good way to put it. Avenarius built on this, focusing on sensory complexes.
Sensory complex.
Yeah, the idea that common sense objects like a table or a chair, they aren't fixed entities out there. They're dynamically reconstructed through our perception.
So it highlights the fluid, interpretive nature of experience.
Exactly. He radically reframed knowledge as this adaptive, emergent process, positioning sensations as absolutely fundamental.
Okay.
This led him to his concept of principal coordination. Basically, the idea that the I and the environment are fundamentally intertwined in experience.
So mind and world arise together.
Simultaneously and inseparably, yeah. Consciousness and the world emerge together. It's a deep dive into neutral monism.
Neutral monism.
It's a philosophical approach, suggesting a fundamental reality that's neither mental nor physical, but capable of generating both. It really challenges those traditional mind-matter divisions.
Suggesting a kind of primordial substance that's neutral.
In a sense, yeah, ontologically neutral. It stands in contrast to something like subjective idealism, which would say reality is only mental.
That sounds incredibly complex. How does that philosophical shift lead to the next big movement, neopositivism, also known as logical positivism? This is Q2 for the exam.
Right, neopositivism. That brings us to the 1920s and 30s. The neopositivists, people like Carnap, Schlick, Reichenbach, they actually preferred the term logical empiricism.
Why logical empiricism?
Because it truly reflected their core philosophy. Knowledge comes only from experience, grounded in immediate sensory perceptions. But scientific understanding needs rigorous logical analysis.
Experience plus logic.
Exactly. Their main goal was to define the true task of philosophy, analyzing knowledge statements to make them crystal clear, unambiguous,
And getting rid of.
what they called meaningless German speculative metaphysics. For them, only meaningful statements had a place in science.
And meaningful mentors.
Either analytic statements, which are true just by their logical structure, like all bachelors are unmarried.
True by definition.
Right. Or synthetic statements, which are factual claims verifiable by empirical evidence. Anything else, like metaphysical statements about God or absolute reality, was considered meaningless.
Why meaningless?
Because they lacked both logical necessity and empirical testability. You couldn't prove them true by logic or by looking at the world.
So they were really trying to sweep away anything that wasn't strictly provable or logically sound.
Precisely. They also pursued physicalism and reductionism, especially thinkers like Carnap. The idea that all sciences, even social sciences, could ultimately be reduced to physics. That their concepts and laws could be expressed in terms of fundamental physical laws.
And reductionism.
The theoretical terms, things like electron or gene, could eventually be reduced to observational terms, grounding all scientific language in directly observable phenomena.
Wow, that sounds like an incredibly ambitious project. Did it work?
Well, this ambitious program faced a huge challenge, finding a perfect criterion of cognitive significance. How do you actually draw the line between meaningful and meaningless?
The verification principle.
Initially, they pushed for strict testability, or verification. A proposition is meaningful only if it's empirically testable, verifiable through observation.
Okay, seems reasonable.
But they soon realized this was way too strict. It inadvertently excluded fundamental universal statement scientific laws like all copper conducts electricity.
Why? You can test copper.
You can test samples of copper, but you can't test all copper everywhere, past, present, and future, so you can't conclusively verify a universal law.
Ah, I see the problem.
And this is where Karl Popper steps in. He famously critiqued logical positivism, arguing that their attempts to eliminate metaphysics accidentally eliminated natural science too by making the rules too tight.
So this is where post-positivism, Q3, enters the scene, with Popper and his crucial principle of falsification. How did that change the game?
It was a total game changer. Instead of verification, Popper argued that a scientific theory must be falsifiable.
Eating.
It must make predictions that can, in principle, be tested and potentially proven wrong. A truly scientific theory, for Popper, welcomes challenges. It's ready to be refined or rejected based on new evidence.
Rather than seeking endless confirmation.
Exactly. It shifts the focus from trying to prove theories right to actively trying to prove them wrong. If it survives those attempts, then it's a stronger theory.
That's counterintuitive, but powerful. And what about Thomas Kuhn's concept of paradigm shifts, which is also a key post-positivist idea mentioned in your sources, though maybe not always grouped under that heading?
Right. Kuhn's idea is huge. He argued that science progresses not just by gradually adding knowledge, bit by bit.
Like building a wall brick by brick?
Yeah, not just like that, but by revolutionary periods where established frameworks, what he called paradigms, are overthrown and replaced by entirely new ones.
Paradigms, like a scientific worldview.
Exactly. A shared set of assumptions, methods, values, standard problems within a scientific community. Think of the shift from Newtonian physics to Einstein's relativity. That wasn't just adding a brick, it was rebuilding the whole foundation.
And this highlights the social aspects.
Definitely. Kuhn emphasized how scientific understanding is deeply embedded within a community's shared assumptions, practices, and even, unspoken beliefs. Science isn't done in a vacuum.
And other post-positivists. Your sources mentioned Lakatos, Feyerabend, Polanyi briefly in the Q3 outline.
Right. Imre Lakatos talked about research programs, focusing on how science progresses through a core set of ideas protected by auxiliary hypotheses. Paul Feyerabend, he was more radical.
Anything goes.
That's his famous line. He argued for methodological anarchy, basically, saying strict rules stifle creativity. And Michael Polanyi talked about tacit knowledge. The stuff we know but can't easily put into words, like how to ride a bike or recognize a face. He argued this personal, unarticulated knowledge is crucial in science, too.
So post-positivism gives a much richer, maybe messier, picture of science.
Much richer, yeah. It moves beyond just pure logic and verification.
Which sounds like science isn't just a purely objective, logical march forward, but something influenced by people and their shared beliefs. This brings us directly to the problem of internalism and externalism in understanding the mechanisms of scientific activity. That's Q4. Is scientific discovery all in the head, or is it shaped by the outside world?
This is a really core philosophical debate. Internalism focuses on the individual scientist's mind.
The inside factors.
Right. Their cognitive processes, logical reasoning, individual insights. It sees science as primarily a product of rational thought. How scientists process information, make inferences, apply methods.
Like the classic eureka moment.
Exactly, the internalist ideal. The breakthrough happens purely due to individual genius, internal cognitive work.
But then externalism comes in, saying, hold on, science isn't just in the individual mind.
Right. Externalism emphasizes the external factors. Social contexts, institutional structures, cultural influences, funding priorities, technological constraints, all the outside stuff.
So it sees science as fundamentally shaped by forces outside the individual scientist.
Precisely. Like how universities are structured, how peer review works, what research gets funded. These external things shape what scientists do and how they do it.
Do the sources give an example?
They give a fantastic case study, the discovery of DNA structure.
What's in a crick?
An internalist view would focus on their intellectual processes, building the models, the logical reasoning about base pairing, their eureka moment when it clicked.
Makes sense.
But an externalist interpretation highlights other crucial factors. Rosalind Franklin's critical X-ray diffraction images, which they used.
Often without full credit initially.
Right. Plus, the intense competition between different research groups, the gender dynamics in science back then, and even the post-war funding priorities that pushed biological research.
So the context mattered hugely.
Hugely. The truth, it seems, is often a complex interplay of both internal brilliance and external context.
Reconciling these views seems tricky. Internalism often assumes objectivity, right? While externalism kind of questions that by showing social influence.
Exactly. It's challenging because they operate at different levels, individual versus group or society, but increasingly researchers are moving toward an integrated approach.
Like distributed cognition.
Yeah, viewing scientific thinking as distributed cognition, extending beyond individual minds to include interactions with other researchers, instruments, even computational systems. It's not just one brain, it's a network.
Does this internalism-externalism debate show up in computer science too?
Oh, absolutely. An internalist view might see algorithm development driven purely by mathematical insights or hardware advances following, say, Moore's law, purely technical progress.
But an externalist view.
That perspective points to things like the open source movement, which is hugely shaped by community values and collaborative norms. Or look at AI ethics, that's massively influenced by public concerns and regulatory pressures from outside the purely technical realm.
So both lenses are valuable for understanding how computer science really advances.
Definitely need both.
This leads us naturally to the relationship between science and philosophy itself. Q5. Are they two separate worlds speaking different languages? Your sources argue emphatically no.
Absolutely not. As Daniel Dennett suggested, there's really no such thing as philosophy-free science. Maybe hidden philosophy, but not philosophy-free.
How so?
Philosophy acts as the, maybe, unseen driver of scientific discovery. It provides the explicit or implicit philosophical foundations that guide scientists' assumptions about reality, knowledge, evidence.
It also examines assumptions.
Critically examines scientific assumptions, like Searle's Chinese room argument that challenges the whole idea of the Turing test as a sufficient condition for true AI understanding. That's a philosophical critique impacting science.
And it can lead to big shifts.
It can even lead to paradigm shifts in scientific understanding. Philosophical thinking can open up new ways of seeing things. It acts as a unifying force, too, bridging specialized disciplines that might otherwise not talk to each other.
And it gives researchers tools.
Tools for conceptually rigorous work, yeah. Especially important now with science getting so specialized.
And critically, philosophy plays a crucial role in the ethical dimension of science.
Hugely important. Ethics, as a branch of philosophy, studies right and wrong, providing the moral compass for scientific conduct. Ethical debates around things like stem cells, gene editing, nuclear weapons. These are fundamentally philosophical debates happening within science.
You mentioned Oppenheimer earlier.
Right, Oppenheimer's dilemma. The lead physicist of the Manhattan Project, quoting the Bhagavad Gita, "Now I am become death, the destroyer of worlds." It reviews the immense power and potential devastation of technological innovation. It challenges researchers to consider the broader human impact, showing exactly how philosophical inquiry thinking about morality, consequences, responsibility guides, or should guide, scientific practice. Okay, so let's broaden our lens now and look at science and other domains, specifically art and religion, Q6 and Q7. How does science relate to these other fundamental human ways of understanding the world?
Starting with science and art, Q6, your sources suggest they're actually complementary modes of knowledge production, not opposites.
Complementary, interesting. How?
Well, both rely on imaginative exploration, right? Generating hypotheses or ideas, having the courage to challenge existing paradigms. They might explore different dimensions, art maybe more aesthetic or emotional, science more empirical, but both aim to expand human understanding and perception.
So different methods, similar goal of understanding.
Kind of, yeah. Exploring reality through different lenses.
Okay. Now, what about science and religion? Q7. That relationship seems more complex historically.
Definitely complex. History shows a fascinating transition. In earlier centuries, religion totally dominated how people understood the world. Everything was God's plan or intervention.
Right.
The scientific revolution, especially with figures like Galileo and Newton, started to shift this. But interestingly, many early scientists were deeply religious. They saw their work as revealing the mathematical elegance of divine creation.
So not necessarily conflict at first.
Not always. Newton wrote more about theology than physics. But by the 19th century, things changed. With the rise of Newtonian physics becoming dominant, and especially Darwinian biology, materialism and physicalism gained huge influence.
Explaining things without invoking God.
Exactly. And modern developments in biology, neuroscience, understanding the brain, consciousness, they significantly impact traditional religious views of the soul or mind.
So what's the key difference highlighted in the sources?
It often comes down to evidence and faith. Science values empirical evidence and, crucially, a willingness to modify beliefs based on new data. It's designed to be self-correcting.
While religion.
Religious traditions often value unwavering faith, belief based on revelation or scripture, which isn't necessarily subject to empirical testing or revision in the same way.
And science operates under naturalism.
Right. Science generally operates under methodological naturalism, meaning it seeks explanations within the natural world, viewing it as a closed, mechanistic system governed by natural laws. This contrasts sharply with religious worldviews that often include supernatural explanations, miracles, divine intervention, etc.
Okay, that's a clear distinction in approach. Moving into another crucial societal role, let's examine the role of science in modern education and personality formation. Q8. In our world changing so fast, science education seems vital.
Your sources say it's paramount, and its role is threefold.
Okay, what are the three?
First, for your personal life. It helps you identify components of a healthy lifestyle, make informed decisions about health, diet, environment, that kind of thing.
Practical stuff.
Yeah. Second, for civic life. It helps you make informed decisions on complex issues like energy policy, climate change, public health measures. You need some scientific literacy to participate meaningfully.
To be an informed citizen.
Exactly. And third, for economic life. It helps you adapt to changes in science-related jobs and the general economy. Skills learned in science, critical thinking, problem solving, are valuable everywhere.
So science isn't just for scientists.
That's the message. It's for everyone navigating a complex world.
And beyond those practical skills, how does it shape us as individuals, our personality?
Science plays a crucial role in personality development, according to the sources. It shapes our intellectual character.
How so?
By fostering critical thinking, encouraging open-mindedness, being willing to change your mind based on evidence, and promoting intellectual autonomy, thinking for yourself. These are essential qualities for scientific inquiry, but also just for modern life.
Good point. Does it affect moral character?
The sources suggest it can, maybe indirectly, by challenging and dispelling historical prejudices or biases that might have been based on faulty assumptions. Promoting a more rational, evidence-based worldview can contribute to moral reasoning.
Interesting connection. But with all this power and influence of science, where do we draw the line? This brings us to the demarcation problem. Science versus pseudoscience, Q26. How do we tell the difference? This seems crucial.
It is crucial. Scientific criteria require methods to be subject to empirical testing and peer review. Science relies on systematic observation, measurement, experiments, and reproducibility. Can someone else repeat your work?
Key test.
In contrast, pseudoscientific characteristics often include claims that are just not falsifiable or testable in any meaningful way. They might rely heavily on anecdotes or testimonials, not controlled evidence.
And they resist change.
Typically, yes. They resist modification even when faced with contradictory evidence. Think about astrology or homeopathy. The claims often stay the same, regardless of scientific testing.
And Popper's falsifiability comes in here again.
Absolutely. As Karl Popper asserted, a truly scientific theory makes predictions that can be tested and potentially proven wrong. It sticks its neck out, welcomes challenges and refinement. Pseudoscience often avoids that kind of risky testing.
So it's about being open to being proven wrong, not just seeking confirmation or making untestable claims.
Exactly. Now let's zoom out again to science as a social institution. Structure, challenges, and ethics. This covers parts of Q28 and Q25. Science isn't just a collection of individual geniuses and labs. It's a complex social system.
Right. It has established norms, practices, collaborative networks, a whole structure that shapes how knowledge is created, validated, and shared.
Historically, how have these communities looked? Q28 asks about historical types,
We've seen various types evolve, from informal and visible colleges back in the Renaissance.
like scientists writing letters to each other.
Exactly. Scholars like Galileo exchanging letters, sharing findings outside formal structures. Then came formally established learned societies, like the Royal Society in 17th century London.
What did they do?
They standardized communication, started journals, formalized peer review, made it more organized. Then came university-based science, transforming universities from mainly teaching institutions into major research centers.
And finally,
Finally, big science. This really emerged in the mid-20th century.
with projects like the Manhattan Project.
Exactly, and NASA's space program. These
Wow.
involved massive teams, unprecedented levels of funding, complex technological infrastructures. Think of CERN's laboratory today, over 11,000 scientists from 100 countries working together.
That scale is incredible. It raises the go big question. Is this always more effective than smaller individual labs?
It's a good question. Your sources highlight big science successes in huge engineering projects, the Human Genome Project, the moon landing. Things with clear, complex goals requiring massive coordination.
But for fundamental discovery,
They question its effectiveness there, noting that breakthrough theories, like Peter Higgs's theory predicting the Higgs boson, often originate with a single scientist or a very small team, not necessarily a giant consortium. The big facility might be needed to test the theory, but not always to generate it.
interesting distinction. A cornerstone of this social institution you mentioned is peer review.
Right, the gatekeepers. Supposedly ensures quality before publication. Scientific work gets scrutinized by other experts in the field.
But it has problems.
Oh, yeah. Subjectivity is one. Reviewers can disagree. Biases can creep in. Editors might make conservative decisions, afraid to publish something too radical.
Reviewers are busy too.
Exactly. Reviewer time constraints mean they might not do a thorough job. And there's even potential for misuse, like authors suggesting friendly reviewers who won't be critical enough. It's not a perfect system.
And then there are the metrics used to judge success, like the impact factor of journals or the H-index for researchers.
Yeah, the impact factor measures how often articles in a journal are cited. The H-index tries to measure a researcher's productivity and citation impact.
This creates pressure.
Immense pressure. pressure to publish, often quickly and specifically in high-impact journals. Rejection rates at top journals can be insane, like 98%.
So good research might get pushed aside.
It can push valuable, solid research into lower-tier outlets just because it wasn't seen as high-impact enough, or maybe it challenged the status quo too much.
Do the sources mention rejected breakthroughs?
They share fascinating examples. Mordell's conjecture in mathematics, Enrico Fermi's crucial paper on the neutrino, the Belousov-Zhabotinsky reaction in chemistry, which showed oscillating reactions people didn't think were possible, even George Akerlof's Nobel-winning economics paper, The Market for Lemons, all initially rejected by journals.
Wow, that's sobering.
It is. And this slavery of the H-index, as some call it, can be unfair. The sources mention Piotr Chmczynski.
His RNA paper.
Right. His single groundbreaking paper on RNA isolation has over 65,000 citations, hugely impactful. But his H-index is relatively low because he don't publish tons of other papers. The system doesn't always capture true impact well.
It contributes to a winner-takes-all situation.
Seems like it, where a few individuals or labs dominate recognition and funding, often based partly on these metrics.
And this leads into commercialization. How research agendas get set.
Yeah, there's a growing concern that research agendas are increasingly set not just by scientific curiosity, but by external forces, corporations looking for profitable products, or political agendas prioritizing certain areas.
What's the downside?
It can prioritize economic prospects over fundamental curiosity-driven research. It can also lead to increased secrecy, companies wanting to protect their findings, and complex intellectual property restrictions like patents.
Which hinders open science.
Exactly. It can hinder critical examination by others and slow down overall progress if findings aren't shared openly. It also feeds into the pervasive inequality in science. Well, structural barriers based on race, gender, socioeconomic background, and geography limit access to funding, resources, and opportunities.
Like the stat about African researchers.
Right, getting less than 1% of global research grants. There are huge disparities in who gets to participate and succeed in science globally. Limits on travel to international conferences, publishing barriers if English isn't your first language.
A rich get richer effect.
A clear rich get richer effect, both for individuals and institutions, and bias persists. A 2017 survey highlighted persistent race and gender bias in U.S. science. 50% of women, 62% of African Americans reported experiencing discrimination.
So the future needs change.
The future of science, as your sources emphasize, really lies in pushing for open science, open access to research, data, methods, and constantly wrestling with these crucial ethical considerations to make it more equitable and just.
Speaking of ethics, let's circle back more directly to scientific ethos and ethical principles of scientific research. This is Q25. Building on our earlier discussion, what are the core ideals?
The core ideals are often summarized by Robert Merton's norms, the Mertonian norms.
Okay, what are they?
There's universalism, evaluating claims based on their scientific merit, not on the race, gender, nationality, or status of the person making the claim.
Judge the idea, not the person.
Exactly. Then, disinterestedness. The pursuit of truth should be the primary motivation, not personal gain, fame, or profit, though that's often challenged in practice.
It's hard to maintain sometimes.
Very. Then, organized skepticism. All claims, even those by respected authorities, should be subjected to critical scrutiny by the community before being accepted. Don't just take things on faith.
And finally,
Communalism.
Yeah.
Scientific knowledge is common property. Findings should be shared openly with the community. Secrecy is counter to the ethos.
but these are ideals. You mentioned they're challenged.
They are often challenged by reality. Universalism is challenged by particularism, judging based on who someone is. Disinterestedness by self-interestedness. Organized skepticism by organized dogmatism, resisting new ideas. Communalism by secrecy for commercial or military reasons.
So there's a tension. What about virtues for individual scientists?
Core virtues include intellectual perseverance. Science is hard. Breakthroughs often require years, decades of persistent work. And intellectual courage, the willingness to challenge authority, to question established paradigms, even when it's unpopular or faces resistance. Think of Galileo.
Absolutely. And ethical concerns go beyond these norms to specific practices?
Definitely. Things like plagiarism, stealing someone else's work or ideas. Conflict of interest is huge, like a climate scientist funded by an energy company or a pharma researcher whose funding depends on getting positive results for a drug. These situations can compromise objectivity.
And discrimination.
Discrimination, denying opportunities, or fair evaluation based on gender, race, or other irrelevant factors. This violates the universalism norm directly.
And again, Oppenheimer reminds us of the larger consequences.
The Oppenheimer's dilemma serves as that stark reminder of the profound, sometimes catastrophic ethical consequences science can have. His destroyer of worlds, quote, forces us to see that scientific research isn't isolated from its impact on humanity. Researchers have a responsibility to consider those broader impacts.
Okay, let's rewind the clock now and trace science through history, starting with the science of the Middle Ages. Christian and Muslim science, that's Q10, often called the Dark Ages in the West, but your sources suggest that's too simple.
Way too simple. It paints a much more nuanced picture of a really complex and evolving intellectual landscape across different regions.
So in the Latin-speaking West, what was the situation after the Roman Empire fell?
There was a significant language problem. Literacy declined sharply. Crucially, very few Greek scientific and philosophical texts were translated into Latin. Key works, like Aristotle's Physics, were largely lost to the West for centuries.
So access to classical knowledge was limited.
Severely limited. This definitely hindered scientific inquiry compared to antiquity. But concurrently, the Islamic world wasn't dark at all, it flourished. It became a major center for preserving and advancing knowledge.
What helped them?
A few things. They learned paper production from Chinese prisoners of war around the 8th century. This was huge. Paper was much cheaper and easier to produce than parchment, making books and knowledge far more accessible.
And the rulers were interested.
Yes, ruling classes and scholars were deeply interested in fields like astronomy and astrology, partly for practical reasons like navigation and timekeeping for prayers, but also for intellectual prestige. This patronage fueled advancements.
And they built on global knowledge, right? Not just starting from scratch.
Absolutely. Arab astronomy, from the 8th century onward, actively integrated Greek knowledge, like Ptolemy's Almagest, which they translated, but also Indian and Persian astronomical traditions. This synthesis led to extensive observational programs.
What did these programs produce?
They compiled over 200 zijes. These were astronomical handbooks with tables predicting planetary positions, eclipses, etc. Really sophisticated work based on observation and calculation.
Any key figures mentioned?
Al-Khwarizmi is crucial. He worked in Baghdad in the 9th century. The word algebra actually comes from the title of his book, Al-Jabr al-Muqabala.
So he basically invented algebra.
He laid the foundations for modern algebra by providing systematic methods for solving linear and quadratic equations. Hugely influential.
And in medicine.
Avicenna, or Ibn Sina, a Persian polymath around the 10th, 11th century. His Canon of Medicine was an encyclopedic work that became the standard medical text in both the Islamic world and Europe for centuries, right up until the 18th.
What was revolutionary about his approach?
He introduced, or at least strongly advocated for, the experimental method in medicine. He stressed the need for controlled conditions when testing remedies, distinguishing between the actual effect of a drug and other confounding factors, a very modern idea.
So why did this golden age decline?
It started to decline around the 13th century. Reasons are complex: political fragmentation of the caliphate, reduced funding and patronage for science, maybe increasing influence of more conservative theological interpretations that were skeptical of Greek philosophy, and external disruptions like the Mongol invasions certainly didn't help.
Okay, so as one light dimmed, another started to glow in Western Europe.
Sort of, yeah. Things started picking up. The university emerged as a new institutional home for learning and, eventually, science. This shifted away from education being primarily in monasteries, starting around the 11th century.
What was different about universities?
They offered broader subjects: the 7 liberal arts, the trivium, grammar, rhetoric, logic, and the quadrivium, arithmetic, geometry, astronomy, music. They attracted more diverse scholars and students. Higher faculties focused on theology, medicine, or law. The church still had heavy influence, especially in theology, but it created a space for broader intellectual pursuits.
And we see the beginnings of experimental science there.
Yes, notably with the Oxford School in the 13th century, figures like Robert Grosseteste.
What did he do?
He developed an early account of an experimental method, emphasizing cycles of observation, hypothesis, prediction, and verification or falsification. He also stressed the importance of mathematics for understanding nature.
And Roger Bacon.
Roger Bacon, also associated with Oxford, made a key distinction between passive experience, just observing things, and active experimentum, deliberate testing and systematic observation to discover scientific principles. He was a strong advocate for experimentation.
We shouldn't forget China either, right?
Absolutely not. Medieval China saw incredible scientific advancements. They invented the world's first mechanical celestial globe driven by clockwork, tracked sunspots centuries before Europeans documented them, developed advanced algebraic methods, and designed complex water-powered machinery like trip hammers for metalworking.
So the whole Dark Ages label is really misleading.
Completely misleading globally. It was a critical era. Foundations were laid through preserving classical texts, Islamic innovation, the rise of European universities, early experimental ideas, Chinese technological prowess, and crucially, intellectual cross-pollination between these cultures, often through trade routes and translations.
That sets the stage perfectly for the next big shift.
hmm
The formation of ideals of modern science in the 15th, 17th century, Q11, and then Enlightenment science in late 19th, early 20th century, Q12. This period marks a truly radical transformation.
It really does. The formation of classical science in the 15th and 16th centuries saw a fundamentally new understanding of the universe start to emerge, challenging centuries of Aristotelian physics and Ptolemaic astronomy.
Key figures.
Figures like Copernicus, who proposed the heliocentric model, Galileo, whose telescope observations provided strong evidence for it, and Giordano Bruno, who speculated about an infinite universe with other stars and worlds, very radical for the time.
What else was happening?
The Gutenberg printing press was revolutionary. It made books vastly cheaper and more accessible, accelerating the spread of new ideas, including scientific ones.
And the voyages of discovery.
Yeah, voyages by Columbus, Magellan, and others didn't just discover land, they transformed how reality was abstracted and represented, especially through maps. Map-making became much more mathematical and precise.
And the telescope itself.
The invention of the telescope around 1608 in the Netherlands, and then Galileo dramatically improving it and turning it to the heavens in 1609 that literally expanded humanity's view of the cosmos. Seeing Jupiter's moons, the phases of Venus, mountains on the moon, it shattered old assumptions.
Incredible. And what happened moving into the Enlightenment period, 17th and 18th centuries? Q12 covers this too.
Enlightenment science saw these new ideas solidify into a coherent worldview. Descartes was hugely influential with his mechanical philosophy.
Everything is a machine.
Pretty much. He explained physical change purely through the interactions of material particles bumping into each other. He saw bodies, even human bodies, except for the rational soul, as complex machines.
And Newton.
Newton's Principia Mathematica in 1687 was a landmark. It explained planetary motion, tides, falling objects, all with a single theory of universal gravitation, operating within a framework of absolute space and time. This really established the classical mechanistic view of the universe as a predictable clockwork system governed by mathematical laws. Q24 touches on this classical rationality.
Leibniz had a different vision.
Leibniz, Newton's rival in developing calculus, envisioned a universal symbolic language, the Characteristica Universalis. He dreamed of a perfectly logical language that could represent all human knowledge systematically, allowing disputes to be settled by calculation. Ambitious.
What else defined Enlightenment science?
We saw the rise of geology as a more systematic science, driven partly by practical needs in mining and metallurgy, and the Enlightenment spirit itself, captured by Kant's phrase about humanity's exit from self-imposed immaturity through reason and free public discussion. Works like the Encyclopédie in France aimed to compile and disseminate all human knowledge.
And scientific institutions grew.
Yes, the Republic of Scientists emerged, a kind of international community. National academies were founded. The Royal Society, 1660 in London. The Berlin Academy of Sciences, 1700, Leibniz was involved. The Russian Academy of Sciences, 1724, by Peter the Great. These institutions fostered collaboration, publication, and standardized methods.
And in biology.
We see Linnaeus' system of classification, his binomial nomenclature giving every species a unique two-part Latin name, like Homo sapiens, brought order to the study of life and is still used today.
What about the chemical revolution?
That was huge, too. The dominant theory explaining combustion was the phlogiston theory, the idea that flammable things contained a substance called phlogiston, which is released when they burned.
But Lavoisier changed that.
Completely. Lavoisier's discovery in the late 18th century showed that combustion wasn't about releasing phlogiston, but about chemically reacting with a gas in the air, oxygen.
How did you prove it?
Through careful quantitative experiments, weighing reactants and products precisely. He showed that when metal rusted, a form of combustion, it gained weight by combining with oxygen from the air. This killed the phlogiston theory.
And he did more.
Yes, he created the first modern list of chemical elements, defined elements as substances that couldn't be broken down further, and really established quantitative analysis and precise measurement as central to chemistry, transforming it into a rigorous scientific discipline.
Okay, moving into the 19th and early 20th centuries, how did science change then? Still part of Q12.
Science increasingly transformed from mainly individual pursuits, maybe with an assistant or two, towards more organized collaboration. Laboratories became more central.
Like Faraday's lab.
Exactly. Michael Faraday's lab at the Royal Institution in London was a hub for groundbreaking experimental research in electricity and magnetism. Institutions like the Royal Polytechnic Institution also popped up, capturing public curiosity with dramatic experiments and lectures. Science became more visible, and new instruments were key.
Crucially important, things like improved induction coils for electricity research, spectroscopes. What did spectroscopes do?
They allowed scientists to analyze the light emitted or absorbed by substances. When applied to starlight, this led to the birth of astrophysics. Suddenly, we could figure out the chemical composition of distant stars. Precision balances also improved chemical analysis. These tools opened up whole new frontiers.
Education changed too.
Yes, university education shifted towards more hands-on laboratory training. Places like the Cavendish Laboratory at Cambridge became world-leading centers for training experimental physicists.
What about biology and medicine? Pasteur?
Louis Pasteur's experiments in microbiology were monumental. He famously challenged the long-held belief in spontaneous generation, the idea that life could arise directly from non-living matter, like maggots from rotting meat.
How did he disprove it?
With his elegant swan neck flask experiments, he showed that broth remained sterile if protected from airborne microbes, proving biogenesis that life only arises from pre-existing life. This work also led directly to the germ theory of disease, revolutionizing medicine and hygiene.
And our understanding of the atom evolved.
Dramatically. At the start of the period, atoms were often thought of as tiny, indivisible billiard balls. Then J.J. Thomson's discovery of the electron led to his plum pudding model, a positively charged pudding with negative electrons embedded in it.
But that didn't last.
No. Rutherford's famous gold foil experiment shattered that model. By firing alpha particles at thin gold foil, he showed that most passed straight through, but a few were deflected at large angles. This implied the atom was mostly empty space, with a tiny, dense, positively charged nucleus at the center, a revolutionary change in our picture of matter.
Okay, we've covered a lot of history. Now let's get into the nitty-gritty of how science actually works. The nature and structure of scientific knowledge. This touches on Q15, Q16, Q17. How do we categorize scientific knowledge, and what are its building blocks?
Right, so science as a system of knowledge is generally seen as cumulative. It builds on prior knowledge, though Kuhn would add, with occasional revolutions. It's fundamentally empirical, meaning it relies on observation, experiment, and data. And it strives for objectivity, aiming to minimize bias and personal interpretations.
Q15 asks about the variety of types of scientific knowledge, empirical versus theoretical.
That's a key distinction. We often differentiate between sensual or empirical knowledge. This is the raw data, the observations coming directly from our sensory experiences or measurements from instruments.
The what we see part.
Exactly. And then there's rational or theoretical knowledge. This is the analysis, the interpretation, the framework that transforms these raw inputs into meaningful understanding. It reveals underlying patterns, laws, causal mechanisms that aren't immediately obvious from the raw data.
So it's the interplay between observation and interpretation.
Absolutely. The interplay between the empirical and the theoretical is crucial for scientific understanding. You need both.
How does this distinction play into the structure of scientific theories? Q16.
Well, logical positivism, as we discussed, had a specific view. They saw theories ideally as axiomatic systems, like geometry. These systems had two parts to their language.
Observational and theoretical.
Right. An observational vocabulary, OV, referring to things you can directly observe or measure, like read, meter reading of 5 px, and a theoretical vocabulary, TV, referring to unobservable concepts or entities like electron, force, gene.
How are they linked?
By correspondence rules. These rules connect the theoretical terms to the observational terms, giving the theoretical concepts empirical meaning and testability. For example, a rule might link the theoretical term temperature to the observable reading on a mercury thermometer.
And theories get power from axioms.
Yes, theories gain explanatory power from their fundamental axioms or postulates, which are often stated as laws of nature. These are general statements, often universal, like, for all x, if x is f, then x is g. Think of Newton's laws of motion.
How are theories built?
The traditional view is often bottom-up, moving from specific observations to broader empirical generalizations, and then formulating general laws that explain those generalizations.
And theories change.
Yes, theory change is central to science. One view is the successional account, where less basic or less accurate theories get reduced to or replaced by more fundamental general theories.
Like the examples you gave before.
Exactly, like Galileo's and Kepler's laws describing planetary motion being encompassed and explained by Newton's more general theory of gravitation. And then Newtonian mechanics itself being shown to be a special case within the even broader frameworks of relativity and quantum mechanics.
This fits the hypothetico-deductive model.
Yes, it fits well with the hypothetico-deductive HD model. In this view, a theory is a system of axioms and theorems deduced from them. The whole system gets its empirical meaning through interpretation via correspondence rules, and it's tested by checking if the deduced observational predictions match reality.
So theories are these complex, interconnected structures we constantly refine. What about the foundations of science? Norms and ideals, and the role of philosophical ideas and principles in all of this, that's Q17. How does philosophy underpin science more broadly?
Philosophical ideas are absolutely foundational, even if scientists aren't always thinking about them explicitly. Epistemology, the theory of knowledge, fundamentally informs how scientists approach inquiry.
Like empiricism.
Right. Galileo's empiricism, relying on telescopic observations to challenge established Aristotelian views, was rooted in an epistemological stance about the importance of sensory evidence.
And logic.
Logic provides the essential framework for reasoning, for constructing arguments, for drawing valid inferences from evidence. Think of Popper's falsification principle. That's a logical criterion for demarcation.
And ethics, as we discussed.
And ethics, guiding responsible conduct. The Nuremberg Code, developed after Nazi medical experiments, provides ethical principles for research involving human subjects. These ethical frameworks are philosophical.
Science operates with laws and theories.
Yes. Laws are typically seen as descriptive generalizations, often mathematical, stating regularities observed in nature. Theories are broader explanatory frameworks that explain why those laws hold, often by positing underlying mechanisms or entities. Both need to be supported by evidence and make testable predictions. Philosophical ideas about causality, explanation, evidence, confirmation, they all play a role here.
Okay, let's talk about the mechanism of generating scientific knowledge, Q20, and the scientific method itself, Q18. How does that raw data actually become new understanding? What are the steps?
It's a dynamic process, not always linear, but we can break it down. It starts with central perception and observation, gathering the raw empirical data.
The inputs.
Right. This data is then transformed by rational analysis, looking for patterns, correlations, anomalies, trying to make sense of it.
Synthesizing.
Exactly. The synthesis of the sensory and the rational creates a more holistic knowledge framework. The process often begins by identifying and framing scientific problems.
How do problems arise?
Through observing anomalies, things that don't fit the current understanding, or by reviewing the existing literature to find gaps, inconsistencies, or unanswered questions.
Then you form a hypothesis. Q21 mentions hypotheses.
Yes, once you have a well-defined problem, you form a hypothesis, a testable proposed explanation. This can happen through deductive reasoning. If X is true, then Y must follow. Inductive reasoning, seeing a pattern and generalizing. Or, very importantly, through abductive reasoning.
Abductive reasoning again. Explain that simply.
Abduction is inference to the best explanation. You observe some surprising fact, and you generate a hypothesis that, if true, would best explain that fact. It's a creative leap.
Like the ulcer example.
Exactly. Barry Marshall observed bacteria in the stomachs of ulcer patients, a surprising finding. His abductive leap was the hypothesis. Maybe these bacteria caused the ulcers, not stress, as everyone believed. It was the best explanation for the presence of the bacteria. It challenged prevailing belief, but ultimately transformed understanding. Okay, so you have a problem, you have a hypothesis. Then comes the scientific method, Q18, to test it.
Often involving the hypothetico-deductive HT model we mentioned. You derive specific, testable predictions from your hypothesis. If H is true, then we should observe P under condition C.
Then you test the prediction.
Right. Through empirical research. This involves rigorously designing controlled experiments, trying to isolate variables, minimize bias, ensuring methods are described clearly enough for reproducibility, or sometimes it involves careful observation or data collection if experiments aren't possible.
What about theoretical research?
Theoretical research might involve deriving new theorems from existing axioms, constructing mathematical or computational models, exploring the logical consequences of a theory without new experiments.
After the experiment or observation,
Comes crucial analysis and data interpretation. Does the evidence support or contradict the prediction? This often involves statistical analysis. Finally, you develop and communicate scientific results, part of Q20, writing reports, submitting them for peer review, and eventually, hopefully, publication. It's a cycle. And this whole process leads to scientific discovery. Q22. Is it always that neat aha moment we imagine?
not necessarily. Though those happen, discoveries can be unanticipated, arising from chance events or accidents, true serendipity.
Like penicillin.
Exactly. Alexander Fleming noticing mold killing bacteria in a petri dish. Or Wilhelm Röntgen accidentally discovering X-rays when working with cathode rays. Pure chance, but recognized by a prepared mind.
Discoveries can also be incremental.
Very often they're incremental, building gradually and systematically on previous research. Lots of small steps rather than one giant leap. Or they can be revolutionary, as we discussed with Kuhn, fundamentally changing the whole paradigm.
And sometimes they're intentional.
Absolutely. Discovery can also involve intentionality, like Jonas Salk's deliberate, methodical research program aimed specifically at developing the polio vaccine. It wasn't an accident, it was planned research.
Q22 also asks about the distinction between the logic of discovery and the logic of justification. Can you break that down?
Sure. The logic of discovery refers to the creative, often messy process of generating new ideas and hypotheses. It involves intuition, imagination, exploring unexpected connections, maybe even dreams or analogies. There aren't necessarily strict rules for how you come up with a good idea.
So the getting the idea part.
Right. The logic of justification, on the other hand, is about rigorously evaluating and supporting those claims after they've been proposed. This involves testing, gathering evidence, using statistical analysis, subjecting the claims to peer review. It's the process of checking if the idea holds up to scrutiny.
How science ensures reliability.
Exactly. It prevents just any wild idea from being accepted. Both are absolutely essential for scientific progress. You need the creative spark discovery and the rigorous checking justification.
So let's talk about justification more. What are the reasons for the acceptance of scientific theories? Q21. It's clearly not just about one experiment being right, is it?
No, it's definitely a more complex process. Several factors usually contribute. First and foremost is experimental validation.
Matching the facts.
A theory must agree with observable facts, with experimental results. And crucially, it needs to be subjected to systematic doubt and attempts at falsification, not just finding confirming instances, which is often easy.
Like the Copernican model.
Right. The Copernican heliocentric model was initially problematic because it seemed to contradict some observations, like why don't we feel the Earth moving? It took time and further work by Kepler and Galileo for the evidence to accumulate convincingly.
What else matters besides evidence?
Mathematical elegance and simplicity can play a surprisingly powerful role. Sometimes the theory is preferred because it's more beautiful, more concise, or mathematically simpler than its rival.
Like EMCA.
Exactly. Einstein's famous equation replaced more complex theories relating mass and energy with stunning simplicity and predictive power. There is an aesthetic appeal there. Theories also gain acceptance through their explanatory power.
Explaining more things.
Their ability to explain a wide range of diverse phenomena, sometimes unifying things that seemed unconnected before, and especially their ability to generate novel, unexpected predictions that turn out to be true.
But aren't there also powerful socio-historical factors at play? Q21 implicitly asks about this.
Oh, absolutely. Your sources highlight the acceptance of Einstein's theory of relativity as a case study?
Beyond the evidence.
Yes, beyond its strong experimental basis explaining the weird orbit of Mercury, predicting the bending of starlight during an eclipse, which Eddington famously observed, there were significant social psychological factors.
Like who supported it?
Studies suggest that younger, more liberal-minded scientists, interestingly often second or later-born children in their families, who are sometimes argued to be more open to challenging established norms, were more likely to support relativity early on.
And opposition.
Opposition in Germany, for example, was partly tied to a strong anti-Semitic movement targeting Einstein himself. So social and political factors were definitely entangled with the scientific debate.
And aesthetic factors, too.
Yes, aesthetic mathematical factors also played a role. Many leading physicists and mathematicians appreciated the theory's internal coherence, its mathematical beauty and elegance, even before its physical implications were fully tested or understood.
Einstein himself valued that.
He certainly did. He famously believed that the creative principle resides in mathematics, and that sometimes pure thought can grasp reality. He felt the mathematical structure itself was a guide to truth.
So acceptance is a blend.
It's really a blend of rigorous empirical testing, mathematical beauty, broad explanatory potential, predictive success, and the readiness of the scientific community, which is itself influenced by social, psychological, and historical factors to embrace a new way of thinking.
Okay, shifting gears now towards the present and future. Let's tackle tendencies of contemporary science, Q13, and its crucial role in overcoming modern global crises, Q27. This is where science really moves from abstract theory to tangible impact on our biggest challenges.
Right. Contemporary science is very much defined by collaborative, often large-scale, data-driven, and highly technologically innovative approaches. There's a strong focus on developing comprehensive, often interdisciplinary solutions to really existential challenges.
Like climate change, energy needs.
Exactly. For instance, in sustainable energy, the sources mention an ambitious goal, like aiming for 80% global renewable energy by 2040. That requires massive innovation in things like advanced photovoltaics, solar panels, huge offshore wind farms, using AI to optimize energy grids for efficiency.
And storage.
And definitely next-generation energy storage solutions, plus huge efforts in just basic energy efficiency. It's a multi-pronged attack.
What about the demographic crisis mentioned in Q27? That seems broader. How does science help there?
Well, it connects to things like sustainable food production for a growing population. Science is tackling this through AI-driven precision agriculture, using resources more efficiently, vertical farming in cities, and genetic engineering to create crops that are more resilient to climate change or pests.
And water.
Water security is another huge issue. Science is working on advanced desalination techniques to make seawater drinkable more cheaply, atmospheric water generation, pulling water from the air, and smart water recycling systems using nanotechnology and IoT sensors to monitor usage.
And health for aging populations.
Healthcare advancements are key, leveraging genomic medicine for personalized treatments, AI for faster and more accurate diagnostics, developing therapies to extend healthy lifespans, not just lifespan itself.
Q27 also mentions the threat of local and nuclear wars. Can science help prevent conflict?
It might seem counterintuitive, as science also creates weapons, but yes, it can play a role. Predictive analytics, using big data, satellite imagery, social media analysis, can potentially help identify conflict flashpoints early.
And diplomacy.
Scientific diplomacy, fostering international research collaborations, can build bridges and understanding between countries, even adversaries. Shared scientific goals can sometimes transcend political divides.
And technology itself.
Technological peacekeeping is an interesting idea, designing advanced communication systems, real-time translation tools, secure verification technologies for arms control treaties, using tech to build trust and manage crises.
So science is really our greatest asset.
Arguably, yes. Driven by discovery, technological leaps, problem-solving, increasingly interdisciplinary collaboration, and translating findings into real-world applications. But it's also about empowering citizens through science education and literacy so everyone can engage with these issues.
This brings us directly to the realm of computer science and technology, which is so central to almost everything we've just discussed. This covers a lot of Qs from part 2 of the exam list, Q19, Q32 onwards. First, let's talk about computer science as an interdisciplinary science, Q32.
It really is fundamentally interdisciplinary. At its core, it bridges mathematics, logic, and electrical engineering. But it increasingly integrates with almost every other field: biology, bioinformatics, physics, computational modeling, social sciences, network analysis, computational social science.
Has it always been like that?
Pretty much from the start. Think back to Charles Babbage's analytical engine in the 19th century, a mechanical computer design, and Ada Lovelace, often called the first programmer, writing algorithms for it. That combined mechanics, logic, math.
And Turing.
Alan Turing's conceptual Turing machine defined the theoretical limits of computation, that's logic and math. His work breaking the Enigma code during WWII was crucial applied cryptoanalysis. Then the first electronic computers like ENIAC in the mid-20th century involved physics, engineering, math.
And today?
Today, it's everywhere. Computer science fuels robotics in healthcare for surgery or assistance, autonomous vehicles combining sensors, AI and control systems, and complex climate modeling running on supercomputers. It's inherently interdisciplinary.
Q43 specifically asks about mathematics and computer science. You're saying math is fundamental.
Absolutely. Mathematics is the very language of computation. The theoretical foundations of computer science rely heavily on mathematical logic, set theory, Boolean algebra, the basis of digital circuits, graph theory, and discrete mathematics in general.
What about other areas of math?
Even areas like linear algebra are absolutely essential for machine learning, computer graphics, data analysis. Calculus is crucial for optimization algorithms, simulation, understanding rates of change in systems. The connection is incredibly deep.
This underpinning supports mathematical modeling.
Yeah.
Q44, right? Using math to represent real-world systems.
Exactly. Mathematical modeling is about creating a representation of real devices, processes, or objects using mathematical terms, equations, algorithms, logical structures.
Why do scientists and engineers do this?
For very practical reasons, to understand systems, predict their behavior, design better solutions, optimize performance. But your sources also mention it's done sometimes for the sheer intellectual challenge and joy of solving problems, of capturing reality in mathematical form.
Is there a standard process for modeling?
There's a principled approach, often framed as a series of questions you ask yourself. Why make this model? What specific questions do we want to answer? What information or data do we already have? What simplifying assumptions can or must we make? How should we represent the system mathematically? What will the model predict? Are those predictions valid when compared to reality? Is the model actually useful for its purpose? How can we improve it?
So it's an iterative loop.
Very much an iterative loop. Your sources call it something like model, validate, verify, improve, predict. You build a model, check if it matches reality, validate, check if the math code is correct, verify, refine it, improve, and use it to make predictions. Then maybe you start again.
What are some key methods used in modeling? Q44 mentions some.
Some fundamental principles include dimensional homogeneity, making sure the units in your equations are consistent. You can't add kilograms to meters. Abstraction and scaling, choosing the right level of detail. You can't model every atom, so what simplifications are appropriate?
And conservation principles.
Conservation and balance principles are huge, like the conservation of mass, energy, or momentum. Or balance equations, saying the rate of change of something within a system equals inputs minus outputs, plus generation minus consumption. And often, modelers try to construct linear models first, where behavior is directly proportional to input because they're easier to solve, although reality is often nonlinear.
Where is mathematical modeling used?
Oh, everywhere. Physics and engineering, fluid dynamics, structural analysis, circuit design, economics and finance, financial modeling, predicting market trends, game theory, environmental science, climate modeling, predicting pollutant spread, managing ecosystems, biology, modeling population dynamics, disease spread, molecular interactions, even the social sciences.
How in social sciences?
Things like agent-based modeling to simulate crowd behavior or the spread of opinions, network analysis of social media connections, modeling opinion dynamics.
Do models have limitations?
Of course.
Yeah.
They always involve simplifications of reality. The quality depends heavily on the availability and accuracy of data, and complex models can face computational complexity. They might be too slow or require too much computing power.
What's the future of modeling?
Integration of different model types, handling massive data sets, scalability, increasing automation using AI, and crucially more interdisciplinary collaboration because real-world problems cross disciplinary boundaries. And growing awareness of ethical considerations, transparency in models, potential biases, accountability for predictions.
Okay, let's zoom into arguably the most talked about area of computer science now. The problem of artificial intelligence and its evolution, Q33. What is AI, fundamentally?
At its core, AI is a field focused on creating programmable computational systems that can perform tasks traditionally thought to require human intelligence. Things like learning, reasoning, problem-solving, perception, language understanding.
Is there a legal definition?
Your sources mention it's often defined legally by its capacity to autonomously process information, make decisions, and adapt its behavior without continuous human intervention. That autonomy is key.
How has it evolved? It seems like it exploded recently.
The ideas go way back, but yes, progress has accelerated dramatically. Early AI in the mid-20th century focused on rule-based systems, expert systems. Then came milestones like IBM's Deep Blue beating chess champion Garry Kasparov in 1997.
That was huge.
Then IBM Watson winning the quiz show Jeopardy! In 2011, showing sophisticated natural language processing. And Google DeepMind's AlphaGo mastering the incredibly complex game of Go in 2016 using techniques like deep reinforcement learning. That was a major breakthrough.
What's driving this recent progress?
A big part is machine learning, ML, especially deep learning. ML allows computers to learn patterns and make predictions directly from data without being explicitly programmed with rules for every situation. Algorithms like neural networks inspired by the brain's structure are key.
And language models.
Natural language processing, NLP, has made huge strides with models like GPT and BERT that can understand and generate remarkably human-like text, enabling things like real-time translation, chatbots, content creation. AI is also increasingly integrated into cognitive robotics, giving robots more adaptive and intelligent behaviors.
But AI comes with significant potential risks and concerns, right?
Right.
Q33 mentions this.
Absolutely. Job displacement is a big one. AI and automation could disrupt many industries: manufacturing, transportation, self-driving vehicles, customer service, even some white-collar jobs involving data analysis or writing.
What about bias?
Bias and discrimination are serious concerns. If AI systems are trained on bias data, which often reflects historical societal biases, they can perpetuate or even amplify those biases in areas like hiring, loan applications, or criminal justice.
Insecurity.
Security vulnerabilities are another risk. AI could be used to create more sophisticated cyber attacks. Autonomous weapons systems raise huge ethical questions, and AI-generated disinformation or deepfakes could destabilize politics or society.
Then there's the really big picture concern, AGI.
Right, artificial general intelligence, AGI. This is the hypothetical future point where AI surpasses human intelligence across the board, demonstrating genuine comprehension, creativity, and self-awareness, not just excelling at specific tasks like current AI does.
Does current AI understand things?
Most experts would say current AI lacks true comprehension or consciousness. It's incredibly sophisticated pattern matching, but not genuine understanding in the human sense.
What if AGI happens?
The consequences of creating superintelligence are largely unknown and hotly debated. Some researchers and philosophers fear it could pose existential risks to humanity if its goals aren't perfectly aligned with ours. It's a major long-term concern driving a lot of AI safety research.
And all this impacts the future of employment.
Massively. It likely means significant workforce transitions, requiring large-scale retraining and education efforts to equip workers with skills that AI cannot easily replicate, things like creativity, complex strategic thinking, emotional intelligence, interpersonal skills. Adaptability will be key.
Okay, shifting from AI to another immersive tech, the concept of virtual reality, Q34. Where did VR come from?
Early VR concepts and systems actually emerged from military and aerospace applications, particularly flight simulators, going back decades. By the 1990s, we started seeing more advanced head-mounted displays, HMDs, and glove interfaces, although they were often clunky and expensive.
When did it become mainstream?
Real mainstream consumer VR adoption started picking up significantly from around 2010 onwards, with the launch of devices like the Oculus Rift, HTC Vive, and PlayStation VR making it more accessible and affordable.
What does VR enable? What's its power?
VR enables incredibly immersive experiences. It can enhance learning by letting you simulate complex or dangerous scenarios, safely think surgical training or firefighting. It can foster deep emotional connection in computer-generated environments, making storytelling or social interaction feel more real, and it can drive behavioral change.
How for behavioral change?
Through therapeutic applications, skills training where you practice in a realistic simulation, and even personal development by allowing you to experience different perspectives.
It's revolutionizing certain fields.
Definitely gaming and entertainment, allowing players to physically interact within digital worlds. Audiences can step inside narratives in immersive films. And education students can take virtual field trips, explore historical events, or visualize complex scientific concepts like molecular structures with unprecedented immersion.
Q34 also mentions therapeutic applications.
Yes, this is a promising area. Pain management VR can act as a powerful distraction technique, reducing the perception of pain during medical procedures, for example. Anxiety reduction exposure therapy in VR can help patients confront phobias or PTSD triggers in a safe, controlled environment. And rehabilitation VR games can help patients recover motor skills or cognitive functions after stroke or injury.
But VR adoption still faces challenges.
It does. Cost barriers are still significant. High-end VR systems remain expensive for many consumers and institutions. Technical limitations persist issues with display resolution, field of view, processing power, and especially motion sickness or cyber sickness for some users. And content availability, there's still a relative scarcity of high-quality, compelling VR applications compared to traditional platforms.
What about the future? The philosopher Chalmers.
Right, looking way ahead, philosopher David J. Chalmers makes a bold prediction in his book Reality Plus. He argues that virtual worlds could become indistinguishable from non-virtual reality within a century.
Indistinguishable. Right.
That's his claim. He argues this could transform our very understanding of experience, consciousness, and existence. He talks about perceptual indistinguishability, if it feels real, is it
Ah.
the ontological implications, can virtual worlds be genuinely real? And technological convergence, things like advanced neural interfaces directly stimulating the brain, maybe combined with quantum computing, could make VR incredibly realistic, a mind-bending future possibility.
Wow. Okay, underlying all these digital advancements, AI, VR, the internet itself, is the critical issue of information security, privacy, and cybersecurity, Q35. What's the core idea here?
It's fundamentally about protecting sensitive information and computer systems from unauthorized access, use, disclosure, disruption, modification, or destruction. It's about ensuring the confidentiality, integrity, and availability, often called the CIA triad of information.
What are the main threats we face? Q35 asks about cybersecurity threats.
They are incredibly diverse and constantly evolving. Common ones include phishing, deceptive emails or messages trying to trick you into revealing passwords or installing malware. Malware itself, malicious software like viruses, worms, spyware, ransomware malware that encrypts your data and demands payment for its release.
And attacks targeting people.
Social engineering, psychologically manipulating people into divulging information or performing actions they shouldn't. Man-in-the-middle attacks intercepting communications between two parties. And zero-day exploits, attacks that target previously unknown vulnerabilities in software before developers can patch them.
How do we defend against these?
It requires a multi-layered approach. Strategies include having a strategic defense framework, maybe managed by a dedicated security operations center, SOC, implementing multi-layered protection firewalls, intrusion detection systems, strong encryption, antivirus software. Crucially, human-centric security regular employee training is vital, as humans are often the weakest link. And adaptive risk management, having agile processes for detecting incidents and responding quickly.
And this all ties back to the modern principles of cybersecurity ethics, the CIA triad you mentioned, Q35.
Exactly. Confidentiality is about preventing unauthorized disclosure of sensitive data, keeping secrets secret. Integrity is about ensuring data is accurate and hasn't been tampered with or modified without authorization. And availability is about guaranteeing that authorized users have reliable and timely access to information and resources when they need them. Balancing these three is key to robust cybersecurity.
Okay, let's talk about the bedrock of much of this, the internet. Let's trace its evolution and profound philosophical impact. Q36, Q37, Q38, Q39, Q40, Q41. Where did it begin? Q36.
Its journey really began with ARPANET, a U.S. Department of Defense project in the late 1960s. It pioneered key technologies, especially packet switching.
Packet switching.
Instead of needing a dedicated connection like an old phone call, data was broken into small packets, addressed, and sent independently through the network, finding their own routes and reassembling at the destination. Much more robust and efficient.
How did it go from military project to global phenomena?
Through the commercialization of the internet. In the late 80s and early 90s, policy shifted, allowing commercial traffic. Deregulation and the rise of internet service providers, ISPs, opened it up to the public. This completely transformed communication, commerce, culture.
Then came the web.
Right. The Web 1.0 era, roughly the 90s, characterized mostly by static HTML web pages, organizations putting up information like online brochures. Early search engines like Yahoo and Alta Vista helped navigate it, but users were mostly consumers of information, not creators.
What changed with Web 2.0?
Web 2.0, emerging in the early 2000s, was the big shift towards interactivity and user participation. The rise of social media platforms like Facebook, Twitter, YouTube was central. It enabled user-generated content on a massive scale, blogs, wikis, forums, photo sharing. It democratized content creation.
And today,
Yeah.
what are the big trends?
Today, we're seeing the massive expansion of the Internet of Things, IoT, billions of physical devices, from smart thermostats to industrial sensors, connecting to the internet, generating huge amounts of data. This fuels big data analytics, transforming how we gain insights and make decisions. And technologies like blockchain are emerging, promising new ways to handle trust, security, and decentralization with things like cryptocurrencies and smart contracts.
The internet clearly transforms society. What about its deeper philosophical significance? Q37, the On Life Manifesto.
Yeah, philosopher Luciano Floridi and others proposed the concept of the On Life Manifesto. It explores how the internet is blurring the traditional boundaries between being offline and online. Our lives are increasingly lived in a way where those distinctions don't make much sense anymore.
Examples.
Think about telemedicine appointments, remote work collaboration tools, augmented reality games overlaying digital information onto the physical world, constant social media updates. We're perpetually connected, existing in a hybrid reality.
This creates an infosphere.
Fluharty calls our environment the infosphere, a dynamic informational environment where digital and physical realities converge and interact. This fundamentally reshapes human perception, identity, social interaction, our understanding of presence, and reality itself.
Q38 asks about the internet as a tool for new social technologies.
Absolutely. It facilitates the creation of vast online communities based on shared interests, identities, or goals, connecting people across geographical barriers. It allows individuals to experiment with creating virtual identities or personas, which can be empowering for self-expression and exploration, but also raises questions about authenticity.
And knowledge.
It's transformed knowledge management. Think of online encyclopedias like Wikipedia, expert forums like Stack Overflow, where people collaboratively solve technical problems. It also provides powerful decision support tools through access to vast data and analytical capabilities.
What about the cognitive, constructive, and technological capabilities of the internet? Q39.
Its cognitive capabilities are increasingly enhanced by AI. Think of search algorithms, recommendation engines, machine translation, chatbots that understand and respond to queries. AI is making the internet smarter.
Constructive capabilities.
These relate to its power for creation and collaboration. Platforms like GitHub allow programmers worldwide to collaboratively build software. Crowdsourcing platforms like Kickstarter enable collective funding of projects. Open innovation initiatives use the internet to gather ideas from a wide audience.
And technological capabilities.
These rely on the underlying infrastructure, vast distributed systems, cloud computing, powerful data centers, and increasingly ubiquitous connectivity through mobile devices, Wi-Fi, 5G, and the growing IoT network.
Q40 highlights the internet as a global continuing education environment.
Definitely. Online learning platforms like Coursera, edX, Khan Academy offer access to educational resources from universities and experts worldwide, often for free or low cost.
MOOCs.
Massive open online courses, MOOCs, have democratized access to quality education on an unprecedented scale, supporting lifelong learning and skill development. Although they also face challenges like often low completion rates and limitations in personal interaction compared to traditional classrooms.
And crucially for this whole discussion, the internet is an information and communication environment for science itself, Q41.
Hugely important. Open access publishing initiatives aim to make scientific research articles freely available online to anyone, breaking down paywalls and promoting wider knowledge dissemination.
And data sharing.
Data sharing is becoming increasingly common and expected. Platforms like Zenodo, Figshare, and institutional repositories allow researchers to share their raw data, code, and materials, which enables reproducibility, allows others to build on the work, and accelerates scientific progress. And collaboration.
The internet obviously facilitates scientific collaboration on a global scale, allowing researchers worldwide to communicate easily, share resources, co-author papers, and work together on complex projects regardless of location.
Okay, finally, wrapping up the technology section, let's address computer and information ethics, Q42. This seems critical given everything we've discussed.
It's absolutely critical. Technology develops so fast, the ethical reflection often struggles to keep up. Your sources mention various ethics codes and frameworks developed by professional organizations like the IEE and ACM in the US, and legal frameworks like GDPR in the EU or the AI Act being developed. Russia also has its information security doctrine addressing some of these issues.
What are the key ethical issues these frameworks address?
Many. Surveillance technologies are a big one. The ethics of widespread facial recognition, government surveillance, employee monitoring software. This clashes directly with privacy rights.
Privacy rights like the right to control your personal data, transparency about how it's collected and used, the right to be forgotten in some contexts. Legal frameworks like the U.S. Fourth Amendment against unreasonable searches, the Electronic Communications Privacy Act, ECPA, and the EU's GDPR try to provide some protection, but technology often outpaces law.
What else?
Intellectual property and piracy balancing creators' rights, copyrights, patents, trademarks, with public access to information and culture in the digital age. the ethics of file sharing, open source software, digital rights management.
And data collection itself?
Ethical considerations in data collection are huge, especially with big data and AI. Issues around informed consent, data anonymization, potential biases in data, transparency in algorithms, fairness in outcomes. Social networks also create specific ethical dilemmas around privacy violations, the spread of misinformation and hate speech, cyberbullying, and algorithmic amplification of polarizing content.
So what's the ultimate goal of computer ethics?
Ultimately, the goal is to find ways to balance rapid technological progress with fundamental human values and ethical considerations, ensuring that software and systems are designed and used responsibly, fairly, and accessibly for all. This demands a really nuanced approach to internet governance and policy at national and international levels, protecting human rights, ensuring security, and fostering innovation in an ethical manner through cross-border cooperation. It's an ongoing, complex challenge. Hashtag tag tag outro.
Wow, okay. What a journey we've just taken. From the philosophical underpinnings of positivism, tracing those deep historical currents of medieval science, the Enlightenment, right up to the really complex, cutting-edge ethical dilemmas of AI, VR, and the Internet today. We've unpacked a massive amount of knowledge here.
Indeed. Our deep dive hopefully has shown you not only the core concepts you'll need for your exam, but also just how interconnected and dynamic the philosophy and history of science truly are. It's not a static subject.
Not at all.
You've seen how theories get built, challenged, accepted, how scientific communities evolve and function with all their norms and pressures, and how technology is increasingly shaping both our understanding of the world and really the very fabric of our society.
So what does this all mean for you, the listener, the learner? You've gained not just facts and names, hopefully, but a framework, a way to critically engage with scientific arguments, to understand their context, and to think about their profound implications.
It's about critical thinking. And maybe remember that quote from the linguist S.I. Hayakawa, your sources included. The symbol is not the thing symbolized. The word is not the thing. The map is not the territory it stands for.
The map is not the territory. I like that.
It's such a vital insight for understanding scientific models and theories. They are incredibly powerful representations of reality, our best maps, but they are not reality itself. There are tools, always subject to refinement, always potentially incomplete.
And science keeps progressing.
Science continues to progress, driven by emerging technologies, increased collaboration, that ongoing relentless pursuit of knowledge. It keeps expanding our understanding of the universe, keeps redrawing those maps.
What's the challenge to them?
The challenge, and maybe the opportunity, lies in ensuring that this incredible progress is always guided by thoughtful ethical considerations, by a deep sense of human responsibility for the knowledge and power we gain.
So the final thought for you to ponder: what new maps will you help draw? How will you use this understanding?